Greetings. So right here, you're going to see a diagram, and that diagram may even be useful to you. And that diagram describes a program that I'm about to show you. And that program transforms Notepad from an ordinary text editor into a bloodthirsty vampire bat. Let's get started. So we've got here Notepad. You've seen it before. This is Notepad. See, perfect. It used to be that every programming tutorial would start like that. People would do things in Notepad because they didn't have a microphone, so they couldn't talk. But now we've got it here, and now Notepad itself can talk as we... Yes, and we hear it squeak. Exactly like a bat. Because it is a bat. This is a recording of a bat. Now, if we look at Task Manager for a moment, you'll see that I've replaced Task Manager with a different tool that looks very similar to Task Manager, but much worse. This is Process Explorer, and I personally prefer it. You can see that there is no squeak.exe running right now, and in fact, squeak.exe has gone away completely. The only way to stop the squeaking is to close notepad.exe. Now, this is just a fun example, but of course, there are other uses for this technique. The general idea of this technique is that if you don't know what process is doing a thing that's not desirable, you can't easily stop the computer from doing the non-desirable thing. For instance, I could be writing a program that is encrypting your files or sending your traffic to another server, and it could be running in exactly this way, and that would be really bad for you. Now, I'm not going to do anything like that in this video because that would be unethical and it would be very frightening. But I think the technique itself is really interesting, and it was used in production in an adware program called Direct Revenue that was written by Matt Knox a long time ago. There's a very famous article about it that's so famous that I couldn't find it when I went looking for it, but maybe you'll be able to find it with the search terms that I've implicitly given you. Now, to start with, we're going to be making a bat noise. We've actually already got a recording, but we're going to trim it down a little bit, and we're going to make it possible for Windows to play using the Play Sound API. Next up, we're going to take that bat noise and we're going to turn it into a C program that can be injected into another program. This is the injectable program. We're going to turn that injectable program into a slug, which is to say, we're going to remove the parts of it that are the least important to running it, and we're going to turn it into a file that can easily be used for other possibly nefarious purposes. Having done that, we're going to give it to a Rust program that will write that program along with a little stub that loads the content of the program, and it's going to put that program right into Notepad, which will promptly start thirsting for blood and biting other text editors. So that's what I've designed for you, and that's what I've written and what I'm going to recreate for you right now. And afterwards, you will have your own exceptionally tiny, only 17 kilobytes, wow. You'll have your own exceptionally tiny program that does exactly what this one does. So let's get started. So the very first thing we need to do is fix up our audio file. This isn't programming, so we need to pull out Audacity. You might have other audio editors that you like more than this, and you're well within your rights if you do like other editors more than this, but this is the one that I like. I also like Ableton, but it feels weird to use non-free software in a video like this, right? So we'll clip this down. We will mix it so that it is no longer in stereo, and that will save some file size. Yes, so that's the gist of the sound. We'll amplify it so it's real loud. You'll notice that there's quite a lot of dead air at the end of that. We'll just, get rid of that dead air. And you'll notice that even after we do the fade out, there's still some dead air. Yeah, that's good. That's a bat noise. Yeah. We'll be exporting it as an MP3 file at the lowest possible quality, which is that quality. I noticed that we've exported it once. We're going to export it again, and we're going to do one other thing to it. We're going to get rid of all of the metadata because we don't need the metadata. So what we have now is this short MP3 file. But one thing you'll remember, or maybe you won't remember, is that I said that we were going to make this playable by Windows' Play Sound API. So to do that, we actually need to make a few more changes to the file. And we'll just go right to the folder. This is, by the way, how you open another VS Code inside of VS Code. It'll work outside of VS Code too. It'll work anywhere. So we'll have a terminal here. So basically, play sound needs a WAV file. The thing is that you can put an arbitrary MP3 file inside of a WAV file, which is what this command does. I'm using the copy of FFmpeg that came with ShareX. You probably have one on your system because it's bundled with a lot of tools, but you can also install it separately if you choose. So this will turn it into a WAV file. We now have that, and it actually sounds a little bit better because all of that high-pitched reverb starts sounding like the bat noise itself. So we'll look at this WAV file. We'll notice that the WAV file is very, very small. It's 3.75 kilobytes. And we'll notice that the WAV file looks pretty much like a normal WAV file up until about this point. So this is the WAV header, and you'll notice that basically the WAV header has a bunch of small numbers that are represented in little endian format, like this is the number 2. Possibly this is the number 2 and then the number 0. I'm not sure how it's packed. And then something weird happens. We have some text. We have this 80040100 sequence, which does not to me look like a series of numbers at all. Those are ominously round and low numbers, except for 80, which is an ominously middle number, I suppose. And just in general, like it takes until about like here for the data. The data starts looking like normal audio data about here. It doesn't look like PCM audio data, like it doesn't look like a WAV file, but it at least looks like audio, and that continues for a while. And then we have the file is screaming at us, and we refuse to listen. You'll also see lame 3.1, which is, I assume, the name of the program that output the MP3 file, because I specifically remember installing that. By the way, this kind of program is called a hex editor. It edits files that contain binary data, and it gives you a view of the hex values, which is to say the 0s and 1s packed into groups of 4. F is 1111, and you've probably seen a hex editor before if you've ever modded games, but I thought I would show you one. Yes, so this is the audio file that we'll actually use. And because we have the audio file now that we'll actually use, we might as well close that up, and we'll return to this folder. So we're going to be writing a C program, and we're going to be using the same tricks that we used the previous time that we wrote a C program. And one of the things that you'll notice about the structure of this is it's kind of like, you can compare it to a Russian nesting doll. I kind of compare it to CRISPR. We're building a tool that acts as a vector to install the thing, and we're also building the thing that the vector installs. And the vector has to be stable. I'm sorry, the vector has to, both the thing that we're creating and the thing that creates the thing that we're creating both have to be stable inside the environments that they live in. And the environments get more restrictive the further we are into the process, but they start out much less restrictive. And anyway, we're building the thing that is at the greatest level of restriction. We're building the thing that lives in the final process. And yet we're going to have access to almost all of C because we're going to create a perfect environment for it. You'll notice that I'm including a file named batclip.h. Such a file does not literally exist. We have it lying around here. This is going to be renamed to batclip.h. Actually, it's going to be batclip.wave. We're going to use a trick to turn it into batclip.h. So this is one that comes from the Linux world, and you can also do it on Windows. C is kind of the same everywhere. That's not quite true, but it's close enough to being true. So if we run our build script, we will get a file batclip.h. You'll notice batclip.h starts for 52, 49, 46, 46. And this file also starts 52, 49, 46, 46. This is hexadecimal, so this is actually 100. Sorry, this is 100 and then 110 in binary. This is, of course, a representation of values that run from 0 to 255 inclusive. You'll see that there are 3,848 of them, which is a number. Maybe it's a big number, maybe it's a low number. It depends on your perspective. The other thing that we're going to do is we're going to build our main executable. And you're going to notice something unusual about this invocation of Zig, which is that there's all this stuff. This says optimize for size. This says do not include the standard library. This says do not link to anything by default. This says please link to kernel32.dll and winmm.dll, which are, of course, reasonable things for us to want because we're going to be using two APIs that are from them. Play sound is from winmm.dll, which is Windows's multimedia API. SleepX is from kernel 32, and what SleepX says to do is it says to wait a given amount of time before your thread is allowed to resume. We likewise will be doing this. This is, of course, our main function. It's got a different name because we can't use the main function that is provided by the standard library. We have to provide one, and it has to follow Windows's convention of returning void. I believe that's Windows's convention. I could be wrong. I think it's Windows's convention. Anyway, we play the sound, and it's the exact one that we've included in the header. We specify that this is memory and not a file name, and then we sleep for a whole second. So if we build this, you'll notice that there's some warnings. Basically, we're turning an array of one type into a pointer of another type, and that's a little bit unusual. But don't get too excited. This is just the injected code, but we'll hear a bat. Right. And to prove that this is different, although I'm sure you believe me, we'll find it in Task Manager and we will... Yep, see, no more bat. This is not resident in the way that we want. Resident being the word that was used in the DOS era for programs that just stuck around. But we would probably say that it has not created its thread, so it doesn't stay running. We need to figure out how to make this very small thing that can survive in the roughest possible conditions. We need to figure out how to make that live inside of Notepad. We also need to figure out exactly what it depends on to stay alive. So before I make the tools to host it inside of a binary, I want to explain to you how an exe file works. You may have seen exe files before. You may have opened one up in Notepad, which is not the best way to open one. The best way is actually a hex editor or a debugger. We'll use both. So exe files start with mz, and they start with this big block of random crap that I believe up until this point is exactly the same on most versions of Windows, maybe all of them. We've got a bunch of garbage here. Who even knows what most of this stuff means? I do, because I had to learn it to make this video. Let's now take a look at this, and we'll find some major landmarks rather than skipping past them. We have here the text section of our program. This is the compiled version of the actual code that we just wrote. Specifically, this corresponds to this stuff. We've got this, which is a jump-off point to reach into the standard Windows code. This one corresponds to the sleep function. This one corresponds to the play sound function. How do I know? Because I've done this before, and I know which one is which, but in practice it's a bit of a mystery. If we scroll on a little bit more, we see that we have a bunch of these CCs. CC is what the Zig compiler will pad this with. Basically, this is an instruction that says, if the code happens to be running in a debug environment, please ask the debug environment to notify the programmer and stop the program and show them. If you're not running in a debug environment, this would normally crash the program. From here, we've got, this is the read-only data section. Most of this is not relevant to us. It's there whether we want it or not. In this case, we actually don't, but it is there. There's some interesting values here. These are a little mysterious. There's basically the value. I already know how to unpack this. You have no way of knowing, but the zeros are part of the value. This is the value of 20A. This is the value of 20AA. They're written backwards because x64 is like that. And yeah, then the read-only data section ends with a whimper. And here, if you're willing to be impressed by it, is the exact audio file that we wrote. It is just copied straight into the executable at the very beginning of what is called the data section. You'll notice, you might remember that it ends with a long, long scream. This is that long, long scream. And as you can see, there's a few other things that have been dumped in there, again, without our consent. Actually, I believe some of these are from another section that we don't care as much about. Those are the major landmarks of the file. And I want to bring you back to this particularly mysterious area of the file. Now let me open this in a debugger and I'll show you a little bit about how it runs. We'll start with a very normal run. We'll just go through it as if there's nothing unusual about it. It opens up a command line window. Of course it does. We'll just head through and we'll resume it a bunch of times and we'll see. Right. So a lot is going on in here. It's actually showing us some code from, I guess from the Windows audio library, it looks like. I wouldn't have known. We'll restart it. Now we've got some code here. This isn't a part of our program. We'll actually go to the beginning of our program. We'll go to it from here. That would be, in this case, the beginning of the text section. It doesn't have to be at the very beginning, but it's usually pretty close to the text section. So we've got here the very first instruction that was generated. We can compare this to the exact output here that is visible in the hex editor. We can see it starts with 55, 56, 48, 83. You can see that 55 is to save the value of RBP. 56 is to save the value of RSI. We create a little bit of space on the stack so that if Windows wants to clobber these values, which is the general behavior of Windows's calling convention, it can. And we find this is the location of the audio file that we have. We'll quickly go to that in the dump view. We can see here, there it is. That's the wave header that I've spent so much time showing you. And there's even the suspicious 80 here. Like, what's that doing there? What's that mean? You don't have to be as suspicious of it as me. I've looked at more wave files than you probably will in your lifetime. That's not true, but I've looked at a lot of them because we use them for various things at work. Anyway, we have this data that's here, but I want to draw attention to something else very, very strange, which is that this pointer here, see, it starts 7FF, 6F, 1D, F4. That's a very strange value because if we look at the actual code, we can see that the LEA RSI part is represented as 48, 8D35. That's all true. And then it represents the location not as this number, but as 2FEE. Now, why would it represent it like that? What does that even mean? Oh, it's a mystery, isn't it? Well, it's not that big a mystery because I know the answer to it. This is the distance between this instruction and if we go to the location in the dump, let's go to it in the dump, not the disassembler. If we go here, we'll see, there it is, there it is. I'm not lying to you. That is exactly 2FEE bytes forward from 100B. This is a relative address. It says add that amount and you have the real address. Now, there's a feature in Windows called ASLR, which means that your program can be loaded at a random location. Basically, like usually like the part to the left here is going to be some random series of digits. It usually starts with 7FF for some reason. I don't know that reason. The right side is usually pretty close to what's in the executable file, but it's not, as far as I know, required to be. So that's 1,000. We've got 1,000 and then some random digits. We don't know the rest of them. The program's loaded here. Very cool. And yes, we're going to use relative addresses so that the only thing that we really care about is the relationship between the positions of these sections. You'll see that each of these is about 1,000 in length. This is a hexadecimal 1,000. It's not the normal 1,000 that you're used to, but it is about 1,000. And the important thing for each of these sections is that the other sections next to it are positioned such that relative addressing works. So what we would say, or what I would say, is that this program is in its starting state. The code that is loaded into memory is extremely similar to the code that exists in the binary here. Like, look for all these CCs. There's the CCs, exactly as I told you that they would be. But this starting state is not enough for the program to survive. The program can only survive if these functions are actually available to it. Now, where do these functions live? They live inside of other DLL files. We can see that kernel32.dll is loaded, but winmm.dll is not loaded. So there's no way for playSound to point to the correct function inside of winmm.dll because it's not there. If we were to go to the location that this jump says to jump to, well, it gets its location from a spot in the RData section. If we go to that address, that one right there, is that the right address? No, that's the wrong address. No, if we go to, sorry, we can get this right, I promise you. So you'll see this corresponds exactly to, sorry, I gotta find it, this spot right here. So right now, that is exactly, or actually, no, it's this spot right here. So right now, before the program starts, this is exactly what is in the binary, but it's not where the thing is in winmm.dll. Now, the reason for that is that we don't know where winmm.dll is yet because it hasn't been loaded. So if we let Windows get to the start of our program, which we have not yet done, now we see that as if by magic, it's not truly magic. We'll go to the exact same place in the dump. We will go to, well, hold up. We'll go to the exact same place in the dump. Yes, now we can see that these pointers, as if by magic, have been replaced by the actual location of the code that it's supposed to run. We can highlight that, and we can look at the memory map, and we can see winmm.dll, its text, its code is loaded at this general category of addresses, 3ED01000 through the next 14. If we go to this in the disassembler, right here, we see that we have actual code inside winmm, and one of the pages of that, it's the one that starts with 9, that jumps to more code inside of winmm. The value is now patched. And if we go back to the code of main, if we go right back to this in the disassembler, we can easily see that, we can see that this address is, yes, let's look at it really closely. I got to look at it closely or else I'll get confused. It is at, excuse me, it's I'm figuring out which of these two it actually is. It is the one at 80. We'll see it is 7F FD 53 45 52 20. Let's remember 52 20. If we follow that in the disassembler, we see, nope, it was the other one. I misled you. It's the second one. So if we go back, we'll go right back to text in main.exe. Sorry, we'll follow it. It is, how is it that I get almost the right answer and then I just mislead you on that last step? It is DO98BO. We'll see that right at the end, I promise you, unless I'm wrong. Yes, DO98BO. It has been replaced by the exact address of the playSound function inside of winmm.dll. Now, isn't that cool? Now we'll just run it again in slow motion so you can see it. See, we'll start it again. Now, main is probably in a slightly different spot, but who can really tell? Oh, we'll restart it again. I went too slow. I was too slow. We'll go right back to our data inside of main.exe. This is a lot less scary than it looks, but it's still scary, so be scared of it. Now, we know that our pointers are going to be in this general department, and we will resume, and look, there they are. They changed. See? Perfect. Different values. How did that happen? We just don't know. Yes. Anyway, so we can now hear some squeaks again. I like them. I think that they're adorable. So having done that, we now know that there are a few stages that the program needs to go through to be loadable. There's a few stages that the environment needs to reach for the program code to survive. 1, the starting state must be loaded. The starting state being loaded means that this text section is at 1,000 something. This RO data section is at 3,000 something. And the actual data section is at 5,000 something. The actual numbers don't matter, but the difference is huge because remember, the differences are represented with relative addresses saying, look 2,000 bytes ahead, please, or look 2,000 bytes behind, please. So the starting state must be loaded 100%. That's very important. Next, all of the imports need to have been done. So we'll go back to our data for a moment, and I'll remind you of what that means. We have here an import of playSound. We also have a reference to winmm.dll. There is data in this file that is not human readable that explains that we want playSound from winmm.dll and we want to put the result here. And we need to do that. So the minimum state required for a PE file to be loadable are the starting state, a bunch of bytes, the entry point position, where to start in the text section. And for this program, it's always 0, just because that's what the compiler chose to do. But it could be anywhere, and we may change it later as part of building our loader. And a list of imports where they are represented as a module name, a list of functions from that module. We'll go with library name instead, because that's the name that I will consistently use for the rest of this project. The good news is that now that I've said all of that, this is done and this works. It maybe doesn't do anything that's particularly interesting, but it does work. And we've still got x64dbg here in case we need it. So let's consider that to be working. We will go right back to this folder where we can see the number of files we have is getting bigger every moment. So we're going to build a Slugifier. The Slugifier takes all of the data in load.txt. We'll move it right here. And it also takes an exe file. We'll make a folder for that. And it will produce a binary. So let's go to the Slugifier, which has a binary. I believe it does. Well, it doesn't yet. It has a PE binary, which is to say an exe file. When I say PE binary, just think DLL file, exe file, file that contains code on a Windows machine or a DOS machine. Yes, so we have that, and that's looking pretty good. What we don't have is any program to produce the thing that load.txt describes. So we're going to fight with Python and lose, but we'll make a valiant effort. Oh, see, I told you I'd lose. I forgot to hit the command that says that all the other commands that I did, I really meant to do them. Because if you say no at the end of the wizard, it deletes all your progress, which is probably what you wanted. Sorry, that's not an equal sign. Okay, beautiful. Poetry add. Let's see, PE file. This is a library that, I'm sorry. How foolish of me. Is it good now? Oh, I already had it installed from earlier. Yeah, poetry, if you make another folder with the same name and create a virtual and start using it, it will just keep it around for you. Like I could ceremonially, if I wanted to, I could remove that. Now we have an empty environment. Now we have a full environment. So this is a program. Well, it's not a program. There's no program in this folder, but in a moment, it's going to be a program. And the very first task that we have is using the information from load.txt. We're going to represent exactly those things that matter the most. Right. The program has a starting state. There is a point in the program at which we start. There is a list of things that the program imports. Now, we're in Python. We are going to need to fight with it a little bit because Python's always like that. We're going to switch to a standard level of type checking. And we'll have an import type, as of course we must. This is the name of a library. It's represented as a C-style string. I say C-style string. Python is going to just represent it as a byte string. But this would consistently be written with a null terminator if you were writing C code. We're going to include, these are some utility functions that I brought in advance for you. All these do is they take a generator and they error out if the generator doesn't have the number of elements that is expected. The reason that we do this is because we're going to be traversing the file in various sloppy looking ways, and it helps to be able to deal with the slop of the process by making assertions. So we have our binary type. We're going to need, and again, when I say PE file, just think exe file, and you're half right, because it can also be a DLL file. So these have an optional header. The fun fact about the optional header is that it's basically not optional because you're not going to be able to run your program if it doesn't exist. Because the optional header has things in it like, where does the program start? What does the program where does the program need to be loaded at? And I don't know who thought that was optional, but I think it's a silly name. So you'll remember that I've been talking about text data and read-only data. And I've even been showing you that in the editor. So now is our chance to actually deal with that. Let's do this, by the way. Python is... So the types for this library are mostly wrong. Mostly wrong isn't fair. The types for this library are woefully incomplete, and that's a big problem. We'll also make that fit on the screen. Eventually, this is going to be a losing battle for us, but we can try. So we want the text section, the data section. This is, of course, kind of sloppy. It's copy pasting, but you know, we're writing this for our own use, and it's at least very clear what's going on. Incidentally, a toddler is screaming outside my window, so consider that a bonus. So some of these are actually capable of not being defined, although for this program, all three will be defined. You'll notice there are some other sections listed. They're generally not relevant. They might be relevant in some other circumstance that I don't understand, but in this case, we really only need the ones that we have. Nothing actually refers to anything outside of them. So yes, we will also require that the section not be null. So obviously this doesn't produce a binary yet, and Python calls us on that, so we'll just say not implemented error. We'll write our entry point, which gets the file that we have. I fortunately already have one lying around, so I'll just use the one that I have lying around. That's pretty cool, right? If you'd prefer to just watch me type all this stuff, I can, but it's not a small amount of typing. Anyway, this should load our main file, and we should... Oh, I see that we're not in an environment that has Python in it. Now we have it. Cool, we get our crash. We expected a crash. Did we expect it to? Oh, we expected it to print sections first. So you'll see some information similar to what we saw before. This is formatted pretty horribly. There's a text section. See, text. There is going to be the text section loaded at a virtual address of 1000. That is relative to an image base value, which we'll get to in a little bit. But basically that goes at 1000-ish. Relative to it, you have the data section, which is loaded at 4000-ish, and you have the R data section that is loaded at 2000-ish. And these could be relocated, but the relationships between them would be the exact same. We can now go back up and we can do the rest of the import process. This is almost sufficient for us to get the starting state value, and it is not sufficient for us to get the entry point or list of imports yet. But we can at least build the starting state using the information that we already have. To start with, we know that out of all of these sections that have a relationship to each other, there is a minimum address. Oh no, what did I do? I don't understand why there's a hotkey to just make Python fail to run your code. Doesn't seem very useful to me. I'll zoom out a little bit so you can still see. Yeah, min address, max address, which would of course be, you might think it's the maximum, but this is the starting address. So we actually have to write a slightly different command here. Yeah. So now we can take our loop, we can, yep, again, like I could be using a formatter, but I haven't bothered to install it yet. We will take that, we will make a buffer big enough to store everything that there is. And now we'll go through all the sections. And we will, oh, I'll just include my code that does this. It'll be obvious what it does. We'll get all the data out of each section. We'll put it into the buffer. Now at this point, the buffer is a pretty good representation of the intended starting state of the program. And we'll, again, see that. A lot of zeros, as it turns out, but you'll see there's our text section. There's the CCs. Does it? Oh no, was this truncated? It seems like this was truncated. That kind of sucks. That's not useful. Oh well, I mean, I don't blame it. It's very verbose, but like you'd eventually see the audio file here if it were working correctly. I I guess we can at least like look at the last 1000 bytes too, just so we can see what they are. Yeah, so we can see the end of the audio file. Like here's the big screaming that it does with all the letter A's here, which is maybe useful to you. I can't possibly say. So we'll now define the starting state as the result after that. That completely wraps up this first agenda item. The next agenda item, the entry point position. That is, in fact, in the optional header. You may notice that I spell it entry point RVA. The gist is that there's a value inside the image called the image base. This is just an arbitrary number that various parts of the image will occasionally refer to. We don't really care about the image base. What we actually care about is what the addresses are relative to. Actually, no, RVA has nothing to do with the image base. Just ignore that I said that. This is relative to the value that the virtual address is relative to. So like if the entry point RVA is 1000 and the virtual address is 1000, then the entry point relative to our min address would be that minus min address. Effectively, we're changing all our relative addresses so that they're relative to this min address that's in our starting state, which is not strictly necessary, but it simplifies things because we only have to think of one value as being 0. Actually, so now that we have these two things, we could just party and see what the entry point is. Let's just see what that is. Right. There it is. And just to prove that like it's not just 0 because I failed to initialize something, you'll see that it would be 1000 or 4096, which is 1000 in hexadecimal. Or sorry, rather, that is the value that looks like 1000 when represented in hexadecimal. That is, of course, correct. That is what we would expect it to be. That is the very start of the text section. Now, lastly, we got to deal with the imports because, you know, we have them. Now, this is some really grotty code. So directory entry import is a list of the import data structure. The import data structure says, first of all, what is the library that we use? And that's in a field named DLL. It also contains a list of procedures and the place that their address should be written to. So if we go through these, so these addresses are relative to the image base, which is a completely arbitrary value that you have to use to find the relative virtual address when you are figuring out where to write these in the overall memory space assigned to the process. It is a silly construction that has no reason to be that way, but there's probably some reason that I don't know, but I find it frustrating. Anyway, just like with the entry point, we want to make that be relative to the min address that we've already calculated. And yeah, I know this getatcher is weird. It's just that they haven't typed their library correctly, and I kind of feel an obligation to respond to that by only accessing things using reflection, which is probably not the Python way, but I'm like that. Someday you will be an old gray geezer like me, and maybe you will feel the same way, or maybe you won't. That's fine too. What's important is that we did get everything. Let's actually, the starting state is really verbose, so we'll just temporarily comment it out so we can admire our handiwork. Now I know what I'm expecting to see. We'll see if I see it. Right, so we've got an import of sleepx from kernel 32. It should be written to 4224. Let me make it more obvious to you where that actually is by invoking Python. Right, so remember that our min address is OX1000. So this is 1080 from that. This would have been equivalent to 2080 in the original binary. Likewise, playsound gets the 2090 spot in the original binary, which that would be the virtual address, but the address relative to min address because text section is the earliest section, is just 1080 beyond it. And we have now a binary, and it contains all of this information. So you might think, okay, we can just load it up and we can be done. And that's 100% true. We could, if we had this inside of an environment that is capable of doing the load. The problem is that we're in Python. Where we want this load to be done is Notepad. So what Python can do is not load this, but it can create a sort of protective shell which contains all of this information in a format that is very easy for programs in other languages to understand. That is to say, it is a representation of exactly this information. And I'll make that representation clear to you while I am writing it. We're going to encode it, and we are going to write it to a file. Beautiful. So we'll be writing a function to actually do the encoding now. The contents of the file are just bytes. They are going to be bytes that are structured in a very particular way that makes it easy to load this. But in Python, because Python doesn't need to understand this, it will just be this completely opaque value. And we'll be using a bytes.io, which is the standard way that you generate a big block of bytes in Python. There's no reason to do it any other way. We'll also be using the wonderful 2bytes function that ints in Python support. We'll be writing U32s or 32-byte unsigned integers. U32 is how Rust spells that type name, and we'll be talking to Rust. The other thing that we'll be writing is zero-terminated strings. You'll notice that these are little endian, which is to say that they're written backwards from how you'd expect. The value 1080 would be written as 80, then 10. And because it would be wide enough to need to be in a U32, there'd be 2 zeros after it. A zero-terminated string is just every byte in the string followed by a 0. We'll see an example of that really soon because I'll actually generate the output. So we'll start by writing the address of the entry point. This is being written first because there are other things that are relative to the entry point that may need to be calculated later. We'll go through all of the imports. Actually, that's not totally true. You could probably write the entry point in a different order, but this is how I've chosen to do it. In the case of arbitrary decisions, you often don't need a better justification. So we'll write all of the imports. And the reason that I'm doing these first is because they are very important to determining the... If you imagine our shell around this thing as a big bubble, they're very important to knowing how big the bubble needs to be, which is important because our Rust program is going to take this slug, it's going to turn a slug into a different representation. It's going to turn the slug into a larger but less simple representation, or sorry, a larger but more simple representation that Notepad's code will be able to interact with. And I will explain what that means when I get there. But for now, the important thing is that the output of the Rust program has a size that depends on all of this information. So we're going to put this up front so that it knows how large to make the location that it stores its output. For now, maybe just convince yourself that this is equivalent, or this is sufficient information to reconstruct all of these facts. I mean, that's not true because we haven't written the length of the starting state and we haven't written the actual starting state yet. But we'll start with this and we'll look at it in a hex editor and I'll show you what it looks like for this particular binary and maybe you'll be convinced by it. We should actually... Is that good? That's probably good. Right. Now, oh, I see I've hit the Python key again. I don't know why there's a Python key. It's never useful. We've seen some output, but the important thing is that we now have a main.dat file. So we can just go right ahead and, oh, where is it? It's in Slugifier, it's in binaries, main.dat. Right. So if we look at our values, we start with 0, that's the entry point. Then we have one 0 terminated string, and that's the name of the library. We have a 0 terminated string, that's the thing that we want to get out of it, the procedure name. We have the address, and then we have a 0 terminated string with no data instead of a procedure name. That means end of procedure list. Then we have another DLL file, 0 terminated string. We have another procedure. We have the address that the procedure goes in, 1090, just like I said. Then we have end of procedure list. Then we have end of library list. And finally, we have the size of the starting state, which is 0 right now because we don't actually produce the starting state. We will improve that a little bit. Now we have the length of the starting state, which is around 4,000 bytes. Now remember, this is hex, so it's actually 16,384 because that's what OX 4000 means. But we'll pretend that it's just a value of 4,000 because it's easier to talk about that way. So to review our file format really quickly, because I don't want you to get too lost. It is for each library and library name, libraries. It is library name is a 0 terminated string. Procedure address. And we'll just tag the types. DT stir is in 0 terminated string. 0, 0. Len starting state. And for good measure, we'll say entry point U32. So this is all the information that we need to determine what the final injected payload needs to be shaped like. You could call it the shell code. You could call it something else. I think I call it the... No, I don't even have a name for it, actually. Gosh, the code never assigns a name to it. So anyway, we'll start with this, though. This is enough that if we only had a representation of the starting state, we should be totally good. Now, I'm going to introduce an algorithm that you've probably seen before and you've definitely heard talked about. This is one of the worst implementations in the world of this algorithm, and I'm very sorry about that, but it's a tricky one to get right because it involves a surprising number of decision points. And mine has several inefficiencies and even one glaring bug, but it's only a bug that affects the compression ratio. It's not a bug that affects the correctness in any way. So we're going to be doing RLE, and the gist of it is that we're going to have two different functions that each represent a choice that RLE could make. And the first one can produce none if the choice turns out to have been a bad idea. And the second one always produces a value because the choice is never ruled as having been a bad idea. Oh, hold up a second. Yes. So we're going to be in a loop. We're going to break out of the loop in a few cases. One, if we're asking a value to be repeated over 255 times, we can encode that. One, if we've exceeded the length of the data, and two, if we've exceeded the length of the data, and three, if we haven't matched the first byte. Let's look really quickly at what this implies about our RLE. It implies that we can have a code of one of these values, and it expands to yes. So for instance, decompress of, let's say, we'll go with 0801 is 010101010101. We'll add a space so it's clear that that's two groups of 4. So that's 8. Right. So that is the repeat block in RLE. That's the happy case. We will also be providing yes. We'll also be providing the ability to mark a list of bytes that must be repeated literally. And that looks a little bit like this. We'll say, right. So the 00 is just the code saying, hey, this isn't an RLE block. Don't use the RLE method on it. The 3 is the number of bytes to repeat exactly. And then you have the bytes that are repeated exactly. So that's a common way that RLE works. We will then say, so out of the repeat case, we'll only ever use the repeats decision if there were at least 2 bytes that might have been a repeat. And we always commit to this in a greedy fashion. We don't even try the other branch if we found a repeat. And we will, of course, as before, we will produce the new value of I. By the way, you'll notice that this loop always indexes at data starting from start. This is basically equivalent to just slicing data by start before we use it, but it's a little bit more efficient because we don't have to allocate a new data. In practice, the efficiency probably doesn't matter. This is Python, but it's a force of habit. So these cases are the same. We don't want to exceed it, we don't want to exceed the length of data, and we cannot encode a value greater than 255, so we won't try. This last case is different. It says that if we do see a repeat break, so this case is actually written, the reason that we might subtract 1 from I in this case is because if we hit a repeat, we actually should start encoding from the first byte involved in the repeat, which would be the previous byte at the time that we notice it. We may try that change in a little bit because it may have some efficiency advantages. Regardless, we always continue in this case. We have no bailout early option. There is an optimization. So if the length is 1, we don't have to write 0 because, as it turns out, O1 of x is equivalent to 0, 0 of O1 of x in all cases. So we'll revisit this likely in a bit, but for now we'll keep the algorithm in the simple and somewhat incorrect form that I have written down. That'll save me some trouble because if it's wrong to make these optimizations, I'll discover after I have an already working program. So yes, we now have the ability to handle both of these cases. So what we're going to do is we're going to simply try both of these two cases at every point in which we need to do some compression. And eventually we're going to run out of data. And that will mean that we have compressed everything. And this should get us a much smaller starting state value than we had before. That's the first case, and as you can see, it's allowed to fail. And that one's not allowed to fail. We always use the value that it produces. So that should be pretty good. And we'll now have a little bit more data in this. Oh no, it froze. Why would that happen? There's obviously a problem with one of these loops because that's the thing that we added, right? Like there has to be, clearly. 1 second, I'll look at these conditions really closely and I'll see if they match my starter program that I already wrote. Oh, right, we never actually advance I in this, so we just pull the same repeat forever. There we go, beautiful. So now we will look at this. You'll see that the file is now a little bit longer, or at least I think it's a little bit longer. You'll see some really embarrassing errors. Like in this case, it got very ambitious when it saw winmm.dl. It got ambitious between the M's, and it got ambitious right before the L. So as far as I know, the better ways to implement RLE involve tracking how much regret you have after some synchronization point. I've done nothing of the kind. This is a very naive implementation of RLE. But as you can see, it still does shrink the value. Like we have now only about 4,096 bytes. Like if we look really quickly at how big main.exe originally was, it was about 7 kilobytes. Actually, I'm curious, like we could just try just for the sake of it. Let's just see what the savings actually are, because maybe they're not as big as I think they are. So in this world, we write the entire starting state, and yeah, so in this world, oh, let's look at the binaries. It's 17 kilobytes. The thing is that like most of the wasted space actually comes from all of these extra zeros that we add just to fill in the holes between these spaces that are plotted into memory. Like It's genuinely not very efficient to just lay these out all in a row because we effectively expand every section out to 4096 bytes and then cover for it. But like we've still done that, right? So that's just kind of wacky. And there's probably a lot of there's probably a lot of avoidable inefficiency here. Like, especially like, look at this. This is how we encode all that zero padding, like 255 zeros, 255 zeros, and it just repeats and it repeats. What's that about, huh? It's wacky. So anyway, we'll move on from that though. We've got at least a candidate of a binary, which means that our Slugifier is satisfying, which means we can move on to the next step. You can kind of see this as like, it's almost like an egg that has not been hatched. It needs to be given an environment in which it can survive. Maybe that's too poetic. Maybe it's just the right amount of poetic. Anyway, we've got this going on here. The next stage of our program is a big Rust program, which is not exciting because, as you know, I don't really like Rust very much. But in this case, it's the right language for the task because we're going to rely heavily on its implementation of generics, and that will save us a lot of time and effort. We do want to, let's initialize the project first because then we'll have a place to put all this stuff. Cargo is, of course, Rust's dependency management tool and build system, and it's a good tool. There's a few tricks that we can do that I want to show off right away, actually. Like, one of the things we can do is we can say that we can just directly include main.dat here. Now, what's this do is it adds this to the data section of the program, actually the read-only data section of the program, just in the way that our XXD trick from C did, but it does so in a nice, terse, and direct way. So we have an injector.exe program that we can happily look at, and I'll just show you that it's been added because I'm assuming that it will have been. So here's injector.exe. If we just look through, we'll see this is just all the random crap that Rust dumps into your program without your prior consent. Like, a lot of these are like error messages from various parts of the Rust standard library. There's the paths of everything. Let's just look really quickly for the phrase riff. Oh, it didn't even include it. I guess it got eliminated. Like, what we can do is we can do this. So in this world, Rust at least has to actually use it. And we can now build it again. Oh, wait. Did the string riff actually go away from it? I bet it became... Because there's a... Yeah, it became riff because look at the repeat. This is, again, just a totally unnecessary inefficiency. There's absolutely no gain from doing this to the F here. I don't know. It's life, I guess. As a side note, I'm giving this the squinty eye here because, like, I guess there's 4 literal bytes here. I guess that would be why. Yeah, presumably. That looks true. Anyway, like, but there's 4 literal bytes. Why does it then immediately... I assume that there's something being doubled up in here that I'm just not counting correctly. I assume it's correct until it's proven to me that it's not. It's a very bad RLE implementation, and I know that there are compression algorithms that are better than RLE, and at least ones that have pre-existing implementations that would save me trouble. Unfortunately, this is what I've got for right now, so we're going to work with it. Now, we're going to do something that is not always considered to be good practice, but I prefer it. We're going to be working mostly in unsafe Rust for this particular program, and that means that you're going to have to see some pretty ugly stuff. So one of the things that we'll do is we'll put our entire entry point in this unsafe main function that I've just invented. Now, if you were writing a production program in Rust, you'd probably end up paring away a lot of the unsafe use, and you'd limit it to specific parts of the program. But we have no realistic way to do this. Now, the other thing I'm going to do that's going to strike you as strange is I'm going to define a function called write imports. We'll do it like that. Now, you might say write them, but we're supposed to load them. We're actually going to load them and write them in one pass, but it's the writing that is a much more complicated operation. So I've named it after that operation instead of the read operation, which is in fact fairly simple because our file format is fairly simple. So we'll provide that function. And one of the things that we need to do to write it, though, is we do need to actually be able to get them. So we'll have a reader type, and I'm going to provide it. It's going to be highly compatible with the Python one. And I'll put the code on screen. It's actually not that complicated, but I don't think it's worth watching me write all of it because it's fairly trivial. I'll just go through the details as I go through. So one of the things is that like it takes this lifetime argument, and that's because I want this to be treated morally as having a similar lifetime to a reference to a slice. This is basically a slice whose boundaries are not known. So we'll implement some functions on it that are very similar to the ones that we used in Python. By the way, I'm not going to make much effort to encapsulate things because this is a pretty short program and it only does one thing. And I think that encapsulation would actually make it harder to understand rather than easier. So this will get a value of any copy type right out of the pointer. And we'll say that the value is equal to pointer dot, oh, we got to import that. Pointer dot read unaligned self dot pointer as const t. Right, so this is a dubiously safe cast, but the type is copy, so it's probably not the worst thing in the world. We'll, of course, also import mem because that's useful. Right, so that'll get you your value, whatever it happens to be. The other thing that we're going to do, and this is a bit of a trickier thing, is we're going to be able to read a zero-terminated string. And specifically, we're going to also read the zero terminator. We're going to include that in our representation. And this is where that lifetime comes into play, because this is a slice with a lifetime, but it's not even close to the lifetime of self. So this loop, of course, well, for one thing, it doesn't actually produce a value of the right type, so we'll mark it like that. This loop remembers where we started reading and then advances self.pointer several times. It reads right up to the null terminator, and then we just want to copy the body once to read one more byte. And that should work. Next, we import slice. Oh, no, I want the one from STD for now. We'll probably use core later, I say, knowing that we will. But for now, it's consistent to just use STD, which stands for standard for the record. So we have, I believe it does at least. I hope it doesn't stand for anything else. So now we have this reader, and it can be used to do the write imports operation. Again, that's like so oxymoronic, but only because we haven't actually written the writer part yet. So there's a few things we remember from our file format. Maybe we should just copy that over just so that we have it here. There we are. So the first thing that we remember is that it starts with a U32. In a way, we're cracking the egg that contains our program. So the next thing that occurs is that we have a list of libraries. We'll do a loop that terminates when we see the first zero terminated string that is just the zero. So that'll get us the name of the DLL. Cool. Now we need to get all the symbols. Right, that's beautiful. Now let's see, what else do we have in here? Like, we do need to get the address too, right? Because if we had the address, then we'd know where to write it. I guess this is the name of the procedure. That's the other way you could look at it. So anyway, the destination is equal to, it is a U32. Now, why is it a U32 and not a U64? You may be questioning that now if you don't remember how we wrote this. This is an offset from the beginning of the blob that we include, and that blob is never going to be more than, it's never going to be 4 gigabytes in size. That would be absolutely insane. We would never do such a thing. So we only need 32 bits to store an index into that blob. So beautiful. We've got that information now. The next thing that we can load that's also relevant to the overall size is the size of the starting state, which I feel like doesn't belong in this procedure actually, because like this procedure is only concerned with the imports. So let's actually just call it there. We'll just do this here. And we will do some mild hackery here. Hold up, you don't like that, huh? Do you, Rust? Oh. Yeah, okay. We'll do it like that. So that should allow us to see an announcement of each symbol. We also want to see an announcement of each DLL. Note that the DLLs don't have a location, just the symbols, or rather procedures. I've called them several names at this point. Right. So if we were to run this now, we would see, oh, right. I'm sorry. I'm still doing this very silly thing of printing that when actually I should be doing this. So we'll just say that the there's a reason that I'll call it that. You'll see soon. I don't need IO read. Why would I need that? Wow, Rust has made a real hash of the imports, huh? So we will then say that the pointer is equal to the buffer as pointer. That's pretty reasonable, I think. Right. Now we haven't written anything, but we can see that it, yes, successfully interprets those imports exactly in the correct way. It has no problem with that. We'll also, for good measure, print out entry point. Right. Now that's, of course, also correct. Now let's go right back to this, because we've actually recorded, when we made this in the first place, we recorded what its basic requirements for survival were, which are that the starting state had to be loaded, the entry point had to be known, and the imports and where they are placed. Oh, and I should say, and where to put them. Yes. We have this, we do not have the starting state yet. The other thing is that, like, while we are capable of reading it, we are not actually capable of doing anything with it. We simply have it. So we're going to do a little bit more logic that goes beyond merely having it. But I feel like before I do that, I should talk a little bit about that write operation, because that'll allow us to kind of put the kibosh on the write imports. We'll be able to say that we've done it all. So I think I'll describe that in just a moment. I think, first of all, I want to create one thing that is an explanation for why I've called this the measuring reader, because maybe you don't understand that yet. So we'll actually have a measure struct, and we'll use this trait. We could call it something else, but this is the name that I prefer. The trait provides, for one thing, this method that takes a slice of U8s and writes them directly. So that's all it does. It will also update an internal counter. In fact, for measure, that's the only thing that it does. We will also be able to write a pointer. This will be implemented the same way for anything that implements this trait. We use core here, but I think I should use std instead. Beautiful. So we will, let's make more of this visible just so you can see. So basically, we'll turn the pointer unsafely into an 8-byte array, which will always work on 64-bit Windows, the only platform we care about. And we will write it using the write function. We will, of course, also be able to see what an offset, such as our entry point offset, actually practically corresponds to in memory in the place where our writes will have been done. So this is a trait that we will be using to build the final stage of our program that is ultimately shipped off to Notepad to be understood by, to be understood in the context of Notepad's hostile environment. We will, of course, implement it for our measure type. And the implementation is not very complicated. We will, when somebody tries to write any slice of U8s to us, we will simply update the amount of space that we know that we need. We will throw out the U8s. And in both cases, if you ask it for an address, because there is no place that these things go, it will reply with the meaningless null pointer address. Now, why do we do that? The reason that we do that is because we want to be able to write all of this data to one of two places. One will be a table of strings that include the names of things that we need to import. One of them will be a prelude, we'll call it. It is a bunch of code that actually does the imports that are needed. The idea is that in this original format, these imports are represented in a way that only code written by me understands. But when we write the prelude program, we will have something that works in any standard Windows environment. It will not require that the code written by me exists because the conversion will have been done. That will be the final element of adornment necessary for the code to work inside of Notepad. So we, of course, have this measuring reader value. The measuring reader will read through specifically the first part, the part that is relevant to determining the size of the thing that we ultimately build. It will read through all this stuff. And I will, I'll give it some measures, which are the type that we've just defined. And yeah, we'll need two of those is what we'll need actually. Let's go with prelude measure actually. Right. So after this is called, we should know exactly how much space it needs. The exact number will be stored in count, and we should be able to say, and you'll see the problem with this in a moment. Right. So now we'll run this again, just as before, and you'll notice the problem, which is that we never actually write anything to strings or prelude. We just say that we will. So this brings in our next programming language, and I hope that you're excited because the next programming language is not assembly. The next programming language is actually machine code, but I'm going to show you using assembly what the machine code does. So we'll be defining prelude.s. This is going to contain a program in NASM syntax, NASM being the assembler that I used to put this together. And the program starts with a very standard function prologue. This is how you start a function. It's really, really common. Right. The one thing that we do that's unusual is that we make an extra 32 bytes. That's 20 in hexadecimal, 32. We make an extra 32 bytes available because Windows APIs really like clobbering the stack of the caller. They want there to be 32 bytes so that when they clobber the stack, you won't care. I cannot for the life of me tell you why that is part of the calling convention. I assume there is a good reason, but I don't know what. Anyway, you're going to see me do something that you never see in assembly, and this will underscore to you that this is only an illustration of how the machine language program works. This is effectively macro syntax. We will say for library in libraries, for procedure in library.procedures, and we'll say destination. There's our Python code that we always write when we write assembly. We will put the library name in RCX. We will put the load library function in RAX. You might be wondering why we don't just call it directly. It's because the call instruction doesn't take an 8-byte operand. You have to put things in a register to call an 8-byte value. So we will load the library. This is morally equivalent to load library a library.name. This is the assembly language representation of that. We will then get the value from our AX. That is the return value. We will, by the way, if you're wondering, RCX and RDX are the first and second arguments, respectively. Procedure.name. And we will now, using these two arguments, I'll just represent it like that. X equals load library A of library.name. We will then get proc address. Oh, I could be a Deltarune character. Get proc address X with procedure.name. Y equals that. We'll just call it Y. Oh, we also have to, how silly of me. Now, lastly, we will say destination is equal to Y. That would, of course, be, I guess, destination, and it's in RAX now. Yes. Beautiful. So this is, of course, enough logic to do all these imports here, but in a very environment independent way, which is probably desirable for us. So next up, we want to call the code that exists inside the binary that we have. Because as a reminder, our requirements were, one, the starting state had to be loaded. At the time that this program is running, that will already have been true because I will have done that from Rust. Two, all the imports need to have been done. This code does that thing. So now our program can run very happily, and it will do so in isolation from Notepad. But to do that, we have to actually jump to the program. So to start with, I guess I'll do it like this. Z is original entry point, call RAX. Beautiful, we've now done. And we can now, yes. So this, and I'll make it a little bit bigger for you, this is our loader. If we can generate this code, and keep in mind that when we generate it from Rust, we're not generating assembler, we're generating machine code, and I'll underscore the distinction as I show you. If we generate this code, we can call original entry point in any environment, including the extremely hostile environment of notepad.exe, which does not have access to such conveniences as winmm.dll. But we have to fucking write it, don't we? So let's get started on that. First of all, we know that a few things immediately go into the prelude. Now, if you're wondering how I know these codes, it's because I went through this with NASM before I wrote the program. So NASM helped me out a little bit. It told me what the codes should be. And if you were to do something like this, you would probably also, I think, write a basic, you would probably write a basic assembly language program and then make it more general, which is what I did. Now, machine language is the thing inside the brackets. It is a bunch of hexadecimal codes. Assembly language is the explanation of what those codes mean. And the assembly language, in this case, I've put that in the right-hand column where you can clearly see it. Maybe you can clearly see it. So we've got some information at this point that we can now use. You'll notice that it's a double loop here. It is, of course, not even close to being a loop here. Actually, we'll use some dots here. Oh, how silly of me. I've forgotten to. Yes, so one of the things that we're doing is we have a strings table for this program. It gets its own strings table because it needs them. So we'll just write the name of the DLL. So this is a pointer that is valid for the generated program that goes to the beginning of the library. Actually, I don't know if we need to actually write a separate null terminator here. Maybe I'm missing something. I thought that we were good on that. Yeah, I don't think we need to write a separate null terminator here. I'll try it without one, and if it breaks, then we'll put that in. I can't think of a reason why that would be needed. So beautiful. We have the library address here. We have the ability to write now a reference to the library address. We know that that's valid because of course it is. We will similarly, so this is a pointer to the symbol that is, or to a string of the symbol that will be valid in the constructed program. So we'll use that in a moment. We can move this up here where it's maybe a little bit more understandable. We have just an unnecessary amount of logging that we'll eventually get rid of. Beautiful. Now we will put the symbol name in. Actually, no, we don't need to do that yet. We should start by. Sorry, I easily get myself lost. I've just realized that I've forgotten to include imports of some functions that we will need. So I will just quickly dump these in here. This won't compile, but I'll fix it in a moment. Those are some functions that we need in order to actually call the functions that we need. Sorry, that's tautological as hell, but we will anyway, we'll put that in RAX, and in a moment we will even know what the value of that is. So this will do the part of this that moves to RAX, and I suppose that we need to... Oh, hold up a second. What the hell is Rust complaining about? I just disagree with that error, actually. Oh, and it went away as soon as I disagreed with it. Right, so we have a value for load library A. Perfect. So now we might as well call it. And that should have that effect. Now, the rest is very similar. We do something like this. You'll notice, by the way, that there's always a 48 byte on these wide instructions. That's what distinguishes them from the non-wide versions. Oh, actually, this is the exact same, so I'll just copy the successful instance of this. Now you'll notice that I'm just considering these constants to be valid in the other process. Reddit seems to believe that kernel32.dll will always be loaded in the same place in every process, so I don't have to worry about any problems where maybe my process disagrees with their process on that. And from what I can tell empirically, that's true. But I don't know why it's true. I don't know if there's some deep reason why it would be true. It's interesting, though, and it means that I don't have to think about things like relocating load library A and get proc address such that it'll work in the foreign process. It's just very curious, isn't it? Anyway. This is the address that corresponds to the offset that we saw in the original file. So like if it says to write it 80 bytes into the binary, this is the actual address of a spot 80 bytes into the previous section of code. For instance, we saw 1080 previously, but like our binary might be located at a super long address starting with 7F like we saw in the debugger. And that would be, of course, a case that we need to handle. And address in binary will, in fact, handle that. Anyway, we've now handled all our imports, so there's really nothing else we need to do with that. We can just write our epilogue. You might already know what that one means because you've seen it so many times. It moves into RAX. And we'll again calculate an address. This is actually the offset to the entry point of the program, which is also in the file that we previously saw. So having done that, we can finally call out to the code that we are writing a wrapper for, which is probably desirable. Now we can leave and return. And that will undo all of the changes that were made in our prelude up here. So that should be, I think also this, yeah. So that should be good, or maybe it will be. And that is our loader. Now you'll notice that the only code that it's written to is code that does measurement. And also we have this horrible thing where all of these APIs from Windows are not recognizably to the program defined. So we actually need to get those dependencies out of Windows. So one second, I'll just quickly create an entry for that in this build script. Or sorry, build configuration, excuse me. And we actually use quite a few features. And this toml editor is going to fight me the whole way as I try to specify these. I believe we use 6. Now that's the one that defines the functions that we needed there, but we'll need other ones soon. Now this is the verbose Rust equivalent of include windows.h. Some people might argue that this is less ergonomic, and I think those people would be right. It does reflect that specifically supporting Windows is not like intentionally made to be the easiest thing in Rust. Like, it's not intentionally made difficult. It's just you're given no help. Anyway, these are the constant locations of these two functions, which should always be the same across all processes. If I wasn't lied to, which who knows, maybe I have been, and if I was, you've got some things to fix. You'll now see that it computes a size of 41 for the strings and 150 for the prelude. Does that seem right? Maybe it's right. The thing that I notice is that I've actually put this inside the wrong loop. This actually belongs outside of the second loop, not just outside the first one. So I think now it should be, yeah, now it's correct. Previously, it would have stopped after doing one set of imports, which is not desirable. And now, as you can see, the prelude only ends once, but we do get all the strings. And I think that's very cool. So, of course, we do have to actually write this somewhere to some unspecified place. And we also have to do the RLE. Let's do the RLE and then we'll do the actual writing. That seems like a good idea to me. The RLE is actually not that complicated, even though the encoder was murder to write. There's no actual decisions to be made when decoding RLE. It's just this straightforward, totally algorithmic process. So you'll just see the code immediately be performable. Oh, excuse me. What I screw up? That's not valid syntax in Rust. It's valid in some languages. I can't remember which. Might be valid in C++. I don't know. I've only written a little bit of C++. So anyway, we're just going to keep consuming until we've gotten enough to fill our buffer. We're going to trust that we've been given a valid RLE set that isn't going to overrun our buffer, which isn't a valid assumption with other people's code. So you'll remember that maybe it'll help if I actually put the RLE format into the project so you can, or no, I have that here. It's right here. Yeah, so we'll handle the case where the code is between 1 and 255 inclusive first. Now you'll notice that we're not using our writer abstraction, and there's no deep reason for that. This is just how I first thought of doing it when I prototyped this, and I never felt a burning reason to change it. So in the repeat case, we get a byte, we figure out how many times to repeat it. We do actually repeat it that many times. You might wonder where do I detect the 0? And the answer is if I'm in this branch, I've already detected the 0. Right. So the logic here is pretty similar across both cases in that both cases write a big run of bytes. The exact details differ a little bit. Now, there's nothing that actually calls this, but at least in theory, if we had logic to write the starting, like if we had logic that invoked this, it would create the third of these major factors that we care so much about. Let's see, soft wrap. There we are. Now we can see much more clearly. Yes, I knew that I could do it. So that's beautiful, and it's probably even useful. But we'll take a look a little bit, and we'll recognize that there's nothing that actually targets a process, right? And it would be nice if there was. So we will quickly yes. And you'll immediately see where this falls over. Also, I don't need to print that now. I mean, I can. It goes right here. Actually, for uniformity, we've basically got 3 sections now. Cool. Yes. And you'll notice that even before we call this starting state function, we know the length of the starting state, and therefore we've done all the calculations without having to traverse the entire thing, which I think is kind of cool. It's not important in this program because this program scope is very limited, but it's a generally useful technique. And you see it in a lot of file formats, that the size of everything is at the beginning in a section where the lengths of things are relatively fixed, or if they're not fixed, at least they're short. Anyway, so we have to now actually write code to identify what process we want to target. So to do that, we're going to use a technique that is also widely used in malware. And this is something that I'm told, but I don't know for sure, a lot of systems will actually attempt to flag you for doing and stop you. Like, it's a very common approach used by malicious coders to figure out what they want to target, presumably. And maybe that's even true. And if it is true, this isn't the best way to identify a target. You could enumerate windows, you could do things like that. But you're probably not actually writing malware, and if you are, you shouldn't be. So I'm not going to cover like more underhanded ways to do this. For that matter, like I'm not going to cover how to bypass UAC, although as you'll see for this program, for some reason, UAC doesn't even trigger. So anyway, what we're going to do, this basically iterates through all of the processes on the computer that your process has access to in a way that is similar to how you would iterate through a linked list. And if it finds one that is recognizably Notepad, it will stop what it's doing and it will leave. Now, all of this weird formality about process entry 32 and maybe uninit, basically, Windows expects that the size of the process entry actually match the size that it expects to see, so it knows that it's safe to do the write. And Rust doesn't like creating a value that is not in a completely initialized state. C has no problem with it, but this isn't C, so we have to use a standard library feature to simulate what C does naturally. The trade-off on this is that C will regularly allow you to leave uninitialized things lying around because C doesn't see that condition as worrying or unusual. So this is a particularly hacky way to, I shouldn't say hacky. This is we'll just go with a way to figure out which process is actually Notepad, because maybe we want that. So as long as we haven't found it, we'll just go on to the next process. Right. So at this point, we know exactly which process we're targeting, because if that function returns a victim, we will use that victim. I think that's cool. So the next thing we do, because there's a lot of next things that we do, we will open that process. We will get ready to do something to it. Actually, why do we bother checking for that? I guess we should check for it because that is one of the ways that Windows signals an error. When we ask for all access, what we're saying to Windows is that we would like it politely to give us the permission to do many bad things to it. And Windows is allowed to tell us that we can't. That's totally fine and valid for it to do. And if that is the case, then this program will just hopefully do nothing. So we'll now figure out, we'll do the thing that I've been promising that we need to do, and we will create a space inside the process where our thing can thrive. Now, I've talked about how the environment is incredibly hostile, and all I really mean by that is, oh, wrong variable name. All I really mean by that is that, like, it doesn't have our imports, and in theory, an exception in any thread of the program can crash our code. In reality, because our code is memory safe and their code is memory space, their code has no way to discover our code, and our code has no way to discover their code. So, in theory, all of it should be able to run in harmony within the same process, as if we just had two separate processes. They happen to share memory, of course, but it's as if we had two separate processes, which is pretty wacky stuff. By the way, you might notice that I'm not doing anything to force the right alignment. Weirdly, I have never had a problem with this strategy related to alignment, and I would assume that something about how I'm invoking this enforces the correct alignment. Maybe it's just the large page size. That being said, I wouldn't be massively shocked if it turns out that there are conditions where this doesn't work and that you need to manually specify alignment. It's not that I think that this is guaranteed to work. I just think Windows happens to work in a way that makes this work. But like a lot of this, I think does exploit a level of undefined behavior regardless, in that Windows, for instance, I don't think ever formally guarantees that kernel 32 will be in a consistent place, and yet as a consequence of its others' behaviors, it is. Maybe that's just me getting on my high horse. I would imagine that that's at least a behavior that enough people depend on that Microsoft wouldn't willingly break it. So, by the way, the only thing that you really need to understand here is that execute read write says that, like, if we write a jump instruction that jumps to the page, the jump instruction will actually work. Anyway, we're now done with our measuring reader, which only read the beginning. We're now going to write a second reader that actually goes through this to the end. We're going to initialize it the same way, of course. So what we're going to do is we're going to take this local address space, which is kind of our staging zone, and we're going to split it into 3 chunks, one for the starting state, one for the strings, and one for the payload. So that's our 3 chunks. We're going to make 3 writers, and I'm going to include the code for that. It's pretty repetitive. I'll go through it, and you'll actually notice that we haven't defined our writer type yet. So the gist of it is that we have a remote, which is existing inside of this process. We've just made it. We also have our staging zone, which is defined by this base and this pointer. So we're going to build everything in the staging zone, but whenever it returns an address, that address needs to be valid inside the binary. So it's going to move the address to be offset relative to the binary instead of relative to the base, which I think is an important distinction. We are going to use these writers, which I'll define the writer type in a moment. We're going to use them. Yes, we'll use them to initialize their respective sections. Oh, yep, there's nothing to import because that doesn't exist yet. And we'll also write our starting state, which is the third of the 3 conditions that we need for our code to survive. And yes, we should now move it from the staging zone to the foreign process. So what this says is that find remote address space inside of remote, copy from local address space, copy a total size number of bytes, and don't bother telling me how many that you're copying. Because in theory, we could give it a site that it could use to report to us how many bytes that it copied, but we don't actually care. We're just going to start the thread, and if the thread dies because it didn't copy enough bytes, so what? Now, there's one last step that we care about, and I'm going to come back to it in a moment after I do the writer. I feel like it is like christening a ship. We should probably do the final invocation as one last step rather than the rather than just doing it because we've reached the point where it would be logically useful to write it. So what I'm going to do is I'm going to implement this writer type. I'm also going to reorder these definitions slightly because it's wearing on me. Yes. So we have this writer type. It has a binary, a base, and a pointer. And it actually does do the writes to the base pointer region, but returns addresses relative to the binary, as I've said that it will. We'll start with this Stockholm, or this, sorry, not Stockholm, this placeholder implementation. This is, of course, just a mem copy, and I would expect the compiler to recognize that, but I'm not 100% sure. There's probably multiple good ways to implement this, depending on how big the list of U8s is. So this is the part where we change the offset of adder to be relative to binary instead of relative to base. Adder is where we started writing, not where we finished, which is why we're using that. Like, that's why we used adder instead of self.ptr, which we otherwise could do. Well, we got to actually return the value. So this offset, like to give an example, this could be the entry point. And in fact, I think that's the main thing that we actually use it for. So now yes, I'm being foolish here. We actually need to do that. Cool. So yes, let's now, if we could, yes, let's write the final invocation. Sorry, I was in my mind going over like what other strange nonsense do we have to do in order to get this to work. I think one thing that I will do is I'll make this return a value. Specifically, it should be a const c void. This will be the actual position that we start at. And the reason that we use that is because we will need to do a jump to that location in a moment. That is the beginning of our prelude. Realistically, we probably should rename write imports to write prelude or write shell program or one of a million other names that we could possibly use. But this is fine for now. So we will now actually create the thread. And I just find this so exciting for the record. Excuse me. You might notice that this is genuinely horrifying. This is basically just me turning a function that is represented as a void pointer into an actual function object, which is not something Rust is happy to do. It's happy to do cast between pointers, but it doesn't really see function pointers as a kind of pointer. Let's see. Right there. I just wanted it to format it so I could read this better. Right. So let's see. We created in the remote. There are no thread attributes. We don't care about the stack size. We will start at the prelude entry point. Well, what? You don't like that? Oh, right, because it's a const pointer. Silly me. Beautiful. And let's see what the, oh, no creation flags. Yeah. The main thing that you would use creation flags for is like if you wanted to create the thread in a state where it wasn't running, which is not a thing we care about right now. So let's actually give this a shot now. We've got a notepad here. Yep, so our program died. We can hear the bat. That sounds pretty good in my opinion. So there's a few other places we can go with this now. I know that's anticlimactic. We've done it and it works great, but I'm not totally happy with it. And there's one main reason, and it's a silly reason, but it is my reason. It's a really big file. 145 kilobytes is just a lot. So there's a few things we can do. One is that we can turn off the standard library in favor of the core library. You might recall that I had some imports from core earlier, but I've generally been trying to avoid using them. That's because I find it very emotionally satisfying to change everything all at once. We go from STD right to core, and not that much changes. All these print line statements do have to go away, because of course they do. There is some representation of this functionality inside of core. I don't really know how it works. I've never used it. Like usually when I'm using core, I don't want to be doing that stuff. I usually want to just be writing the kind of code that I'd be writing in C anyway. There's a few other problems with this. You'll see it when I try to compile it. One is that there is no panic handler in this program, which Rust requires. So I will quickly add one to start with. For some reason, there's always a test configuration, and the test configuration always expects to be using STD, presumably because it is needed for the test library. But the effect is that if I write a panic handler and I don't remove it from, if I write a panic handler and I don't remove reference to it from the test configuration, it won't work. You'll notice that it needs me to change the way that my program actually handles panics to this other setting. I fortunately got that setting written down. It's a little bit obnoxious to remember the incantation for it. In fact, I've got a few build settings that I'll just throw right in there because of course I will. So we've got the panic on abort that's enabled in dev configuration. We also optimize for size. We strip the binary. We do link time optimization, meaning that it's going to try across crates, which are what Rust calls libraries, to reduce the code size. And codegen units, supposedly this changes binary size. I'm willing to bet you it doesn't, but I'm not willing to bet you a lot, so I won't bother with it. And now we see that there's one other problem, which is that the entry point is not defined. We told Rust no main. We didn't give it a main. We gave it a function named main. The thing is that if you take out std, that's no longer the main function. There's nothing that calls it. So what we actually need to do is we need to replace this with the thing that Windows expects main to be called. Which for some reason is different here. I don't really understand why. It's a mystery to me. But we now have a function that Windows can call. This should do nothing. Yep, Notepad's not running. Beautiful. Yes, so we'll close this. Yes, and I want to look at the file a little bit more with you. I want to show you that now the file is only 15 kilobytes, which is nice and small. So there's a few other things we can do. One of the things that I threatened to do is I threatened to make the slug smaller. We'll see if those optimizations that I threatened to make actually work, although note that this still takes us very far away from an efficient implementation of RLE. We're still not even close to that. Anyway, that would be one of the things that you could do. The other thing you could do is right, Python main.py, please. Oh, excuse me, you seem to have... What? No, that should exist. I'm sorry. Well, I mean, you say that, Poetry, but, like, you sure? Okay, so now we've got that. We've got a binary. We'll look at its size. It's now 4.04 kilobytes. What's the old one size? Do we know how big it is? This one is also 4, or no, that's the same one. 4.04 versus, dare I ask, 4.08. Okay, so it didn't make a big difference, but it made a little difference. We'll see if this one actually works. Not, we'll just hopefully return it to the previous version. Right, that didn't actually... Okay, so those changes work great. And there's our bat noise. Yep, the other thing we can do is we can look at this. Did that make it any smaller? No, it doesn't matter because the size is actually fixed to a certain multiple of itself. We will go back to this folder here. Right, so this is the injector. We can look at the code really fast. We can see that it's a standard binary. Then this is the actual, I believe this is the text section of our program. It's admittedly, I still find this to look weirdly huge. I don't know why it's so big. We've got the binary that has been generated by our Python program, which is shaped like a thing. And then we've got, why is there a reference to injector.pdb? That's not what I want. That shouldn't exist. Like, I don't know if I can fix it right now, but it's like weird that that's in there, right? Yeah, there's clearly more stuff that could be stripped here. Some of this I'm just going to blame Rust for, but like it should be possible to make this way smaller. That being said, 15 kilobytes is, it's fairly small. There's always the pursuit of smaller, right? Anyway, we can name it squeak.bat, of course. Now, is it a batch file? No, it's just funnier to name it that. And to verify, like, yeah, that still works. Yeah. Now, there's one other thing that I want to try. And if it doesn't work, the video is going to end right here. And that's not true. The video is going to end in a moment. I'm going to try it right now. So to start with, we'll save our file. We will change the logic of this a little bit. Let's see. That looks good. Now, you might ask, why would you do this? And the answer is that I really like the bat sound. And I don't want anybody else to be left out of the bat sound. And I think that you might like the bat sound too. So we'll simplify this logic a little bit. So the thing is that when we have a callback function, and this is important to understand, we can effectively return more than once. Let's see. Hold up a second. I need to write this as a closure, apparently. Or maybe I don't. Like, there's nothing stopping me from just changing the logic to be like this, actually. Yeah, okay, cool. So that probably works. So we will... Yes, so this is a scarier program than the previous one. It's also shorter. So in a moment, I'm going to stop my recording and then I'm going to start it again. And the video will end if this program blows up my computer and I can't use it anymore. Because what this should do is it should take every program on my computer and make it squeak like a bat. And that might crash OBS. It'll certainly be really loud. So I'm going to stop it and then I'll start it. One moment. Okay, so we're in the section that if this works, you're going to be able to continue watching. This is going to be really, really loud, by the way. because it's all going to happen at once and will. Yeah. So you'll notice that no matter how many processes I close, this is still going to keep happening. You'll also notice that, yes, despite the fact that all of the processes on my computer are doing this, it remains very usable because, as I said, my code is very memory safe. Now, there is absolutely no way that my computer can be used at this point. Like, I am going to have to reboot because everything is making bat noises, literally every process on my computer. There's nothing I can kill that makes this go away. There's absolutely nothing that I can do about this. My computer is completely fucked. And I think that's really cool, right? Because like normally in Task Manager you could deal with this. But here you just fucking can't, and it makes you wonder, why on earth does Microsoft make this sort of thing possible? Thank you, Microsoft.